Welcome everybody to this coffee break. I am your host today. My name is Louis-Daniel, and we are live here in the office in Quebec City. And today our topic is orbital welds and how to inspect them using eddy current array. So as an introduction to orbital welds, it was developed in the 1950s for the aerospace industry, and it was mainly for welding very thin tube and very small diameter tube, which are challenging to do manually, by an automatic arc welding machine that rotates around the tube. And this allows a very precise and a beautiful weld. It's very repeatable as a process. And as you can see right now, this is just an example. It's very smooth and it looks flawless, but as every weld, there's always a possibility that there are some defect inside, such as crack or porosity. And this is why they need to be inspected by non-destructive testing. And traditionally, the two methods that were used for inspecting these types of weld are radiography or X-ray, and also dye penetrant. For X-ray, it is a very precise method. It allows a detection of very small defect, very small porosity, very small cracks. However, it is very time-consuming. For inspecting a weld like that, you need to take different acquisition from different side of the weld, and there's also security measure to put into place when inspecting a weld like that. So overall, the time required to inspect a single weld like this using X-ray would be around 50 minutes, more or less. So it's very time consuming, but that's a method that traditionally worked very well. The other method is dye penetrant. Dye penetrant works well for surface breaking defect only, but it's take much less time than X-ray. There's also a concern of having contaminant since you're using dye on the weld, but overall it would take around maybe 15 to 20 minutes to inspect the weld. Now, the goal of eddy current in this case would be to reduce that inspection time as much as possible and to keep the detection capacity and performance as high as possible. So before going to much depth on performance of the ECA probe, let's look at what types of weld that we're going to be inspecting, what are the different parameters. So type of material that we're targeting with this probe is most non-ferrous material that are used in the aerospace industry mainly. So titanium, stainless steel, zirconium, Inconel. They all are also aluminum, I think this is also possible. So depending on the material that you're using, you might have to tweak a little bit the frequency of the probe that you're being used, but it should work for all those non-ferrous material. Weld thickness that we're targeting, so more or less 0.5 millimeters to 2 millimeters. If it's thicker than that, then perhaps a bigger color is going to be required, but this is the target that most orbital weld, the thickness is going to be within that range. Minimum defect length that we're targeting here. It says 1 millimeter, but depending on the material and the defect criteria that you're using, we can tweak the probe and the setup to make sure that we're able to find a little bit smaller than that using our eddy current probe. And of course, we're targeting both cracks, porosity, depending on their size, might be able to be picked up by the ECA probe also. And of course, the access is always from the outside. All right. Oh, I forgot to mention, if you have any question, don't hesitate to let me know in the chat, and I will do my best to answer those at the end of this presentation. Thank you. The probe themselves are designed to inspect a range of tube diameter. For the smallest tube diameter, 1/8 of an inch and 1/4 of an inch, these are so small that we had to design the probe specifically for both of those diameters, just because the coil and the shoe of the probe where the sensor array is needs to be designed especially for those diameters. For greater diameter, starting at 3/8 of an inch to 5/8 of an inch, we have this probe, for example, they have right here, that can inspect this specific range of diameters. And for greater diameters, we have two other probes that work up until 2 inches diameter. For everything that is 2 inches and more for orbital weld, to be more cost effective, we have a different way of inspecting it. It's use the same coils actually, but it's just inside a standard probe, a standard padded probe that can be fixed on the holder that clamped around the orbital weld, just like this probe, but the same probe can be used with a different holder depending on the diameter of the orbital weld that you're inspecting. And it still allows a precise and a stable scan, just as with this probe. Now let's look a little bit more in detail inside this probe and what are its features. So first of all, eddy current wise, it used 2 millimeters coil in short double driver topology. This is very good and optimized for surface breaking detection. The only probe in their standard catalog that do not use a 2 millimeters coil for the orbital weld probes is the 1/8 of an inch probe, which, because it is such a small diameter, since we're using a transmit receive topology, the angle between the transmitting coil and the receiving coils is too wide if we had to use it on a tube that is 1/8 of a diameter. So this is why for this specific probe, the 1/8 inch, we need to use 1.1 millimeter coils in short double driver also. But this one, and as the other one, are all 2 millimeters coil centered at 500 kilohertz. The coils themselves sit inside a rigid shoe that is spring loaded. So if I can press it, it is spring loaded, which allows that when you close the probe around the tube will sit directly on the array, and it allows a stable scan with minimal liftoff. To ensure stability during the scan, there are 4 wheels inside the probe. So there's 2 on each side, on the exterior of the probe here, and there's also 2 more on the top, that sits on the top of the probe. And those are connected with a shaft that is connected to an encoder, okay, which comes out here. So the encoder allows you to encode a scan and know the position of the crack. It allows you to use filters. So this is why we use an encoder that is inside this probe. On the top, if you look on the top of the probe, you can see that there's a small window here. This is to allow you to see the weld center line. So if I place my sample here, so as you close the probe, you will be able to still be able to see the weld center line as you're closing, and make sure that your weld center line is placed within that sensor area. Okay. It also shows you the coverage of the probe. So the coverage of the probe for all probe is roughly 14 millimeters. So this is the inspection zone that you're looking for. The probe body itself is made of aluminum and PEEK, so it's quite robust and still lightweight. To open up the probe, there's a small thumb screw here on the side of the probe, which you can just rotate and it will open. And the opening and closing mechanism is actually just 2 rails on each side that are linked with a screw that goes through both sides here of the probe. The standard probe comes with a 3 meters cable and is protected by a protection sleeve like this one. So this is an overview of the features of the probe. But you're perhaps looking for, if you have special needs in terms of criteria or accessing a very tight access area, there are ways to customize the probe, the size of the probe, and its detection. So for example, if you're looking for more of a subsurface inspection, the standard offering is a short double driver, as I mentioned before, and this is very good for surface breaking. It can also detect a little bit of subsurface, but that's not what it was optimized for. If it's something that you're looking for, because you're looking to replace X-ray, for example, it is possible to customize the coils inside this probe, which means we could have both short double driver for surface breaking defect and simultaneously long single driver topology for subsurface detection. There's also different combination of coils arrangement that we can use to either increase the sensibility of those probe to smaller defects, for example. The size of the probe is also customizable, so you can have an idea of what the size of the probe is. So it's roughly 2-inch long, 1 inch wide on each side. But if you need to inspect a well that is hard to access, for example, you might need the probe to be either shorter, for example, in which case we can make it wider but shorter, or on the opposite, we can make it longer but a little bit thinner, for example. So those are the kind of customization that we can do for these kinds of probe, and to make sure that it's tailored to your need and to your criteria. So now let's see the probe in action. Let me start magnify and show you what the probe can do. Okay. So I have a sample here with defect. There's 2 notches in this well. There's a actual notch and there's a transverse notch. Both are a little bit more than 1 millimeter long. So if I just insert the sample inside the probe and I just close it. Now I close it until I feel some resistance here. I don't need to close it that much. As I said, there's a spring-loaded shoe, so once it reaches that sensor array, you will feel some kind of resistance. There's no worrying about tightening it too much. The probe body itself is designed, there's 2 grooves on each side that protects the sensor arrays. So if you close it a little bit too much, the tube is gonna reach that side of the probe and you won't be able to push it further. Now like that, the probe is pretty stable. I cannot move it on either side. I can just rotate it. And looking at the body of the probe, there's a small arrow that indicates the scanning direction that we can use for this probe. So let me null the probe. And if I do a small rotation, there it is. So I have here 2 defects. In magnify, there's 2 C-scan, one on the top and one on the bottom. I will explain to you what these represent. So those who are not familiar with the short double driver topology, that means that I have channels that are sensible only to actual defect, and I have another set of channels that are sensible to transverse defect. So on the top, I have my actual channel, and you can see in the C-scan, the red zone means that there's a defect here. So this is the vertical amplitude that represents the notch that we can see on the right side in my impedance plane. And as I move to the transverse defect. It doesn't appear in the actual, but only shows up here on the transverse C-scan. And you can see on the impedance plane that beautiful crack right here. Okay. And depending on the material that you're using, depending on the frequency also that you're using, you might get different results. But this is to give you an idea of the detection capability of the probe itself. One last thing, I also wanted to mention that right now I'm using the octane, but the probe is also compatible with our portable unit, the Eddy. So that is it for the demonstration. Now I think it's time to take some questions. So let me look at the chat. So what is the maximum depth at which a defect can be detected by eddy current array? This is a very good question. Normally, a rule of thumb for a custom probe that is designed for inspecting subsurface defect, we could go to roughly 40%, more or less. It really depends on the material that you're using. If you're using a high conductivity material, for aluminum would be the worst case, then you would be limited on the depth of penetration. There's also a way to tweak the frequency of the probe to try to get down in depth as much as possible on conductive material. But for everything that is inconel and titanium, for example, it is possible to go down to roughly 40% in terms of depth of the thickness of the tube. And if your tube is more than, that's valid up until a 2 millimeter thickness of the sample. Beyond that, there might be a way to increase the coil size, for example, depending on the specific application. Do all orbitals use an actual scanning direction? So it is possible to use a transverse scanning. Those probes were not designed to have a transverse scanning. The scan is doing actually. The main reason for that is if you're trying to do a transverse scan on an orbital weld, the fact that there's the weld will alter a little bit the electromagnetic properties of the material. And when you're nulling the probe, you're nulling all channels on different part of the weld. And so you're having a much better signal to noise ratio when scanning actually than you're doing transverse. We did some tests. It is possible to use, we could design a probe that do it transversely, but you get a much better signal to noise ratio doing an actual scan. So this is why we use it like that. Which industry? The industry is used, the probe is used mostly in the aerospace industry. So both, mostly in, not so much in aviation, but everything that is spacecraft. It is, we've seen a lot of use for these kinds of application. I know there's some other application, pharmaceutical, and but the most of them that we see are aerospace industry. So it's used both when they are manufacturing a component, so an assembly of tubes using orbital welding, and you need to inspect that right after just when it just weld. And we have also application where it's on-site inspection, so or maintenance inspection. So both of those applications for the aerospace industry. So which equipment do we need? So it works both on the octane tree, and it's also work on the Eddy. You need a Eddy 64 if you want to use the most the subsurface version, the customizable version, but you can also go by using just a 32 if you're using the standard probe. Okay. To copper, it's a good question. What about the performance on copper? Copper would be much more conductive than most of the material that we tested. and that we see for this kind of application, it wouldn't be impossible to do. However, because it is highly conductive, you will be limited in the depth of penetration and detection of that probe. So this is something that you can tweak a little bit using lower frequency. However, you're going to be much better at finding a very, very small defect on copper just because it's so much conductive. So what I would recommend is, depending on your need, we might have to have a customization option where we use maybe a lower frequency coil depending on your detection criteria. But it would be possible, yes. Okay, well, that's all the time we have. I want to thank you so much, everybody, for attending this coffee break. And hopefully we'll see you next time. And until then, well, I wish you good luck on your inspection, everybody. Thank you very much.